Hi everyone. So here we are at the creep test. We're going to have a look at what's happened. It's been 5 days that our samples have been clamped, and once again this is a bunch of different materials that are of interest to us as instrument makers. And we're checking the creep or memory. We could call it either one. Memory, of course, would be these pieces of wood remembering that they used to be straight. And creep would be the permanent deformation of these pieces in response to the load that we have applied. And I'll point out that although this piece of material isn't perfectly straight, it's kind of straight. This bench is better. A little hollow, but pretty close. And then we can see over here, the wood has induced a curve in here, which is about, oh gosh, it's almost 4 millimeters or 150 thousandths or so over this length of this straight edge, which is 2 feet. So let's unclamp it and see what we got. Okay, so first let's just have a look at this. So we're kind of checking the resistance to creep of this material. Which seems to be pretty good. Maybe it might have moved a little bit, but it's curved about the same distance over here as it is over here. Again, no big deal, just a matter of curiosity. And then, see if we can find a place on the bench that's pretty straight. Well, the bench is a tiny bit hollow. We could check with this. We know this isn't straight. All right, let's try this one. Here's a piece of mahogany, and we're gonna measure the deflection here. The permanent deflection after 5 days of load looks like about half a millimeter, 20 thousandths. Okay. So that's pretty good. Here's a piece of curly mahogany. And it's about the same, maybe a little bit less. Here's some Douglas fir. Okay, a little bit more. So far, all of these pieces of wood are a victim of creep. There's another piece of Douglas fir. This is tight grain, and this is very fine grain Douglas fir. About the same. They're all roughly 20 or 30,000. Oh yeah, this balsa wood. This was a little bit of a joke, but this is a lot. This is yeah, 4.5 millimeters, maybe over 200 thousandths. Here's hard maple. And hard maple's a little bit more. This one's probably over 1 millimeter. Here's some curly soft maple, about the same as the hard maple. Yeah, more than 1 millimeter, about 50 thousandths. Here's some Sitka spruce. Point 0.7 millimeters, maybe. 35 thousandths. Another piece of Sitka. This one's about 1 millimeter. And here's some white pine. Oh, all those conifers are about the same. Let's see here. Well, in some ways it's a little tough to know because as a guitar repairman, I know that maple creeps because of all the fender necks I've had to straighten out and repair. Not that other mahogany necks, like Gibson necks, are not impervious to creep, but we can see here that all of these materials have crept a little bit in response to this bending condition where we loaded it. What is that? Oh, maybe around 300 thousandths or 8 millimeters deflection. And it remembered roughly 10% of that, say. Which isn't too bad, but we do see that all of these materials were unable to remember being straight after this stress test. So all of these materials were deformed. And it's a weakness of wood, and it's not terrible, but it's something that we either have to take into account or we have to modify the wood somehow. So taking it into account would mean that when you're creating the neck, you would remove a little bit of extra material from the second octave of the neck and let it not touch the straight edge down here, and you can see that that's what I've done on this neck. There's about 0.7 of a millimeter or 30 thousandths of room on the end. So what we've done, this neck does not have an adjustable truss rod. That's not what I'm using anymore. I'll explain why in a little bit, but this neck is designed to pull up and be exactly the right shape that is very nearly straight so far as the string is concerned when the string load is applied to it. And that means that we have to anticipate the bending by shaping the neck accordingly. In other words, to let the end of the neck fall off or slope downwards a little bit so that when strings are applied, we get whatever it is we want, relatively straight condition, that is. Okay? And then the other thing we can do is to modify the material. And in a way, you could think of this as designing and constructing a new species of wood. So if all of these species, many of which we are happy to use for neck material, like maples and mahoganies, right? All of these materials have responded by not remembering perfectly. And you can see that the maple is doing a little bit worse than the mahogany, quite a bit worse than the mahogany. So maple has a memory that's not as good as the mahogany. Mahogany, very nearly straight. Hard maple, you can see there's quite a bit of movement there. Okay? That's a difference that as a repairman, I was able to notice that the mahogany necks tended to behave better in this area of the neck, where the neck normally transitions into a heel shape, whether it's an acoustic guitar or an electric guitar, there's some kind of transition there, and it induces a stress riser in the system so that there'll be some kind of bending, permanent bending there. So again, we see here that mahogany has a better memory than maple. All right? And that's after only 5 days of distortion. What I tried to do was to design a neck that would use wood, because wood sounds good, and we can vary the wood to change the sound if we like. So this represents the Douglas fir, or softwood core, as you can see here. This black material here is the carbon fiber and epoxy resin, special epoxy. And then on the outside, for the player to see and feel, is a layer of curved veneer. And then, of course, here's the fingerboard, which is yet to be glued to this one. The fingerboard, and then, of course, here's the fret. The benefit of this is that we've created a structure that is very stiff and also very resistant to creep, because carbon fiber and a good epoxy, strong epoxy resin, together in that composite configuration, carbon epoxy, is almost completely impervious to creep and has a beautiful memory. This is great. It means that we can choose the materials that we want to use for their suitability to the purpose at hand. For the fretboard, it would be resistance to being worn out and a nice slippery feel for the player. And for the back of the neck, it would be an attractive material that would feel good, again, feel good to the player. And then in the center, a reasonably lightweight material that sounds good and also doesn't weigh too much. So these materials are combined in the process that I use to make the neck. And here's a finished one. This one's missing its tuning pegs right now, but otherwise is a finished neck. And this is what I'm building for my guitars at this point. This one has a pickup and a carbon fiber pickguard that's faced with ebony. It also has ebony on the front and the back of the headstock to reinforce the softwood core. And you can see here, nice vertical grain softwood core of, in this case, Douglas fir. All right. Here's how it works. Start out with a thin piece of material. Usually I use material that is the same material as I use for the sides and back of the guitar, so it all matches. And this is Italian chestnut, curly Italian chestnut. The thickness of this piece is about 1.5 millimeters or 60 thousandths. And then here's that same material with some linen glued to it. Those of you who watched my videos on bending sides have seen how this works. So we put just a little bit of epoxy, just enough to wet the linen, and then we bond the linen to the outside of the wood surface, and then that allows us to bend the material across the grain like this so that we don't have any cracks or breaks in the material. And the way it does that is it assumes all the, or very nearly all of the tensile load of that bend. So when we're bending across the grain, the linen, which is disposed in plus or minus 45-degree angle, is going to assume the tensile load from bending it across the grain and keep the material from cracking. That's how that works, and of course I'll demonstrate this. And then there's a core of Douglas fir, my favorite material for this. So it's basically a neck shape, but a little smaller than a neck. And that goes in here in the mold. This is a mold that I made in 2005. I basically made it by hand in my milling machine without a CNC program. I just milled it out and sanded it and shaped it the way I wanted for a net shape on the outside of the neck. And since I made it, it has picked up a little bit of complexity, but I'll show you how this works and what the components are. First of all, it's 2 big pieces of aluminum, about 2 by 4 inches. And into one side I've cut the room for the neck joint. This is a structure that helps me to hold this pin in the right place, and this pin is secured here with a screw, and then it gets cut off in the right length so that it becomes the center of the neck pin. And the function of that wood really is not to add strength so much as to force all the carbon fiber and epoxy into the corner of the mold so that I don't have any holidays or open spaces here. And it compresses the carbon fiber closely together so that I get a good fiber to resin ratio, and it makes a really nice structure. You can see a lot of it gets cut away in order to install a piece of machinery, a little bushing with threads in it that allows me to adjust the neck up and down. Okay. So this part of the mold is added on in order to be able to force the Douglas fir core material in this direction. And the reason for that is to ensure a tight joint between the end grain of the veneer and the end grain of this part of the neck. And I think you can see here how beautifully that works. That's just a clamp to clamp the core up against the veneer so that I get a beautiful joint there. There's a strap across the end of this so that holds the veneer, keeps it from slipping out the end of the tool. And when it's all done, it has a shape like this at this end. So that's hand fit to fit the end of the neck. And then down here it has a square hole that lines up precisely with the hole in the tool. Okay? And on this part you can see that that allows the carbon fiber to go through this veneer. And speaking of carbon fiber, here it is. There's 2 tubes. One goes inside the other, of course. And then this pin goes inside there, and it's held on with a wire tie, and that is in turn held in this little fixture. It helps me keep the wooden dowel pin in the right place. So when it's assembled, the carbon is wet with resin, and then it's pushed up through the mold like this. I slit these 45-degree glass fibers in order to let the carbon split, and so half the carbon goes in this direction and half goes in this direction. The neck core comes on top and crushes down on top of the carbon fiber and resin with a big clamp like this, which kind of mashes it all together, at which point the heaters are turned on, which are cal rods, that is electric heating rods that are running the length of this tool. So those get plugged in and the whole thing warms up. And when it comes out, it's all cooked up and nice and hard, and it's all bonded together. There's no voids, there's no bubbles. I did have trouble with bubbles for a while, and I ended up being able to fix that with a pump, so that the last thing I do before we put the mold away to cure, the last thing that happens is I use this little grease gun and a fitting in this tool, the clamp part of the tool, and I pump resin through the neck pin, and that fills up all the little holes that might be bubbles in the neck pin. I can see the resin dribbling out the bottom, and I know that it's going to work okay. So, and this is the part that comes off this end of the tool. You can see the little carbon fibers sticking out, and get a good look at the cross section of this part. There's more to this, but I promise I'll show you the whole thing in real time, wet with resin, and we'll make a neck together in front of you so you can see how all these parts go together. There's a lot going on. And I've learned quite a lot about doing this in the last 18 years I've been up to it. What I will say is that it creates a neck that has a very high resonant frequency, and it's very, very stiff. This is a tremendous amount of carbon fiber to put in a neck, and I get a huge amount of rigidity in the neck joint. This is just massively stiff connection from this pin to the neck structure. What that enables the neck to do is to transmit a great deal more of the energy than a regular neck. And it means that there's lower energy losses, so it adds some power to the guitar. I'm very happy with it. The system works great. You get a perfect neck joint. You can always depend on the neck joint's relationship to the rest of the neck. It comes out automatically from being molded. And finally, because the resonant frequency is high and the stiffness is so good, it does not support a lot of unwanted resonances, which can lead to either hot spots, in other words, unusually prominent or loud notes, or dead spots, notes that are a product of conflict between the note you're trying to play and the vibratory behavior of the neck. I'm very happy with this method. I haven't had a single failure. It's really worked out great, and it was well worth the year or so it took me to figure out how to make the first one. Anyway, this is my journey to a good neck. It takes into account all the things I learned as a repairman and all the experiments and experimental instruments I built in the 70s, 80s, and 90s. And I'm happy to show it to you. It's a good thing.